So in today's class we will study mainly cosmology. Okay, so cosmology, let me just first go through the specification. What are the topics in your syllabus in this cosmology chapter? If you can, as you can see here, the topics that we need to study are: first, describe the past evolution of the universe and the main arguments in favor of the Big Bang. So we will study the Big Bang theory and the past evolution of the universe. Okay, and then describe evidence that supports the Big Bang theory. So we will like the Big Bang theory. Why is that theory our established theory? Because the Big Bang theory is supported by two evidences. Okay, redshift and cosmic microwave background radiation. Okay. And then describe that if a wave source is moving relative to an observer, there will be a change in the observed frequency and wavelength. This is called Doppler effect. We will study this. This is the equation of Doppler effect. And the redshift, we will study why distance is away from the Earth and also how redshift provides evidence of the expansion of the universe. Okay, so let's begin with story because stories are always exciting to begin with. So in the early 20th century, astrophysicists discovered that the galaxies in our universe are all moving away from each other at great speed. Alright, when was it? In the early 20th century. 20th century means, as you know, it's 1990s, right? So in the early 20th century, so it's like sorry, in the 1900s, I mean in the 1900s. So in the early 20th century is like 1910, around that time. So astrophysicists discovered what? That the galaxies in our universe are all moving away from each other at great speed. So that's an interesting observation. They said that's interesting. So everything is moving away from us. Does that mean we are the center of the universe? Oh my god, that would be like, oh my god, why are we so important? We are at the center of the universe. Everything is moving away from each other, from us. Well, that's not quite right. We will get to that in a minute. Now, this is due to the fact that the space in the space in our universe. This is due to the fact that the space in our universe is expanding. So the space is expanding. Now, I want you to understand this. How do we understand the expansion of space? Well, think of a balloon. Let me just pull this up. Yeah. So obviously I cannot draw a balloon, so I'll just take a picture of a balloon from Google. That's our advantage of live class. I don't need to draw my horrible drawings on board like I used to in class. I can just pull up an image from Google and use it just like that. Okay, so this is a balloon. And also, let me take the picture of a deflated balloon. Alright, like this one. Yeah, so it's basically the same balloon, right? The red balloon, at first it's deflated and then it is inflated. This is before inflation, this is after inflation. Now if you think about this balloon and you take one dot in it, okay? So like if you take one, let me just make this image just a little bit larger. So if you take a dot in this balloon, like a very small dot, just like that dot in that balloon, then let me fill it up. Let's make it black. Yeah. Okay. So there's a dot in that balloon, and then there can be another dot in that balloon here, right? Now, when you inflate the balloon, right? So you take this end in your mouth and you inflate the balloon. Then the balloon will become something like this, right? Well, in this, the shape, the sorry, here this dot might be somewhere like, oh my god, yeah, okay, let me just take it. Yeah, so this dot might be somewhere here, but this dot might be somewhere, like this dot might be somewhere here, right? Now you see these two dots on the deflated balloon. This is the deflated balloon. Let me write this down here so you understand what I'm trying to say. This is the deflated balloon, and then this is the inflated balloon. So after inflation, keep that word in mind. This is after inflation, right? So I can even draw an arrow here indicating like what happened in between these two states. Well, what happened is inflation happened. What happened is inflation, right? So inflation, after inflation, what happened is the balloons, the dots in the balloons are now farther apart, right? But understand, the dots did not really move, did they? The dots did not actually move. What happened is the space between the dots, that is the fabric of the balloon, that space got extended. Correct? You understand what I'm saying? The dots in the balloon did not actually move, but the space between them increased because of inflation. I think you can even find a picture like this in your book. Oh, actually, there's a picture like this in the reading material. Let me just bring that up here. Yeah. So this is what I'm trying to say. You see, a good way of picturing the expansion of the universe is to think of a balloon with galaxies drawn on its surface being inflated. Alright, so this is the inflated balloon. As the balloon expands, every galaxy moves away from every other galaxy, since it is the space between them which is expanding, not the galaxies themselves. Understand? So like think about, for example, let's say this is our galaxy, the Milky Way galaxy. Okay, and those are all other galaxies, right? Or let's say this is our galaxy, and then those are the other galaxies. Now is this galaxy at the center? No, it's not at the center. Like there is no center, right? On the surface of a balloon there's no center actually. So this galaxy, now if you think about this galaxy when it is here, if you are in this galaxy, that is the Milky Way, so we are here, right? We are in this galaxy. Now we see that every other galaxy has moved away from each other, from us and each other, right? So all the galaxies are moving away from us. So we think like, oh my god, we are at the center. No, 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 no. Hold that thought. What if you were in this galaxy? That means you were in this galaxy. The other galaxies were close to you, and now the other galaxies are far away from you. Same, right? So we on this galaxy, we are feeling like every other galaxy is moving away from us, but someone on that galaxy will feel the same, someone on this galaxy will feel the same, someone on this galaxy will feel the same, because every galaxy is moving away from each other, because actually none of these galaxies are actually moving. None of these galaxies are actually moving. What's happening is the space between the galaxies, in our analogy the balloon fabric, that is what is increasing. It's the space between the galaxies that is increasing. The galaxies themselves are not moving. So when I say in the early 20th century, astrophysicists discovered that the galaxies in our universe are all moving away from each other. That's what it seemed like. It seemed like all the galaxies in our universe are moving away from each other at great speed. But what is actually happening is the fact that the space in our universe is expanding. It's actually the space that is expanding. The galaxies are that is why the galaxies seem to be moving away from each other, because the space of our universe is expanding. Is this point clear so far? Any questions so far? um the background or how universe expand, I guess. Okay. The background of is space expression is like a chewing up its expansion, and at last it just chew. Well, that's a very good question. Is the expansion like a bubble gum? Like when a bubble gum expands, at one point it just blows up, right? Is that gonna happen with space? We're gonna find out eventually. Okay, we will answer that question. Hold that thought. That's a very good question. That's an excellent question. Hold that thought. We will answer it in the next few classes. The inflation of the universe infinite. Is the inflation of the universe infinite? Again, same question. Hold that thought. So when the balloon is inflated, the spaces between the dots increase. Exactly. Yes, precisely. That's exactly what's happening. To going to another galaxy is becoming harder and harder. Yes, definitely. Definitely becoming harder and harder. Why the space is increasing? Excellent question. Why the space is increasing? Well, I'm saying the space is increasing, but why? That's where we are still trying to figure out. It's something called dark energy. We will touch it at the end of the chapter, but actually, the simple answer is we don't know. That's the simple answer. I will give a more elaborate answer near the end of the class. Okay. Now, another excellent question. At the start, we all were close to each other, so there were more pull from each other, right? So, and the last question is why space is expanding, like I said. So, Sharia asked this question, you asked this question that, okay, I get it that the everything is expanding, and that's the first thought that comes to mind. That okay, if everything is expanding and moving away from each other now, then it must be that they were moving away from each other before, and they were moving away from each other even before. So does that mean there was a time when every galaxy were like really close together? Hmm, that's an interesting idea, isn't it? What if all the galaxies were really close together? Well, there's a problem with that. The problem is if all the galaxies are really close together, the temperatures will be really high, the gravitational pull will be really high. How was the universe back then if that was the case, right? So yeah, that's exactly what astrophysicists also thought. So let's explore this a little bit more. Okay, so more recent evidence, like in the 1980s, 90s, such as the discovery of the cosmic microwave background radiation. This is something we will study later in the class. Suggests that this is best explained by the Big Bang theory. Okay, so this theory states that our universe was in an incredibly small space about 13.8 billion years ago and supports a number of predictions for the future of our universe. Okay, so basically that's what the Big Bang theory says. The Big Bang theory is trying to say what you just suggested it a little bit earlier, that if space is expanding between all the galaxies, that means like long ago all the galaxies must have been in really close to each other, right? So therefore the universe, that would mean the universe was in an incredibly small space, right? then we can calculate that okay, now the universe, now the galaxies are moving away at this speed. Then 10 years ago the galaxies were moving away, the galaxies were a little bit closer. 100 years ago the galaxies were a little bit more closer. Million years ago the galaxies were even more closer. So by that we can calculate when was, based on the current rate of expansion, that okay, understand this is very important. Based on the current rate of expansion, it's like if you see a balloon and someone is inflating the balloon, you look at the balloon and you think okay, now the balloon is expanding at this rate. So let's say he's a really slow person to inflate, so it's like taking years for him to inflate that balloon. So you're like okay, he is inflating at this rate, then you can kind of guess how much like long ago he started to inflate the balloon, correct? And at that time all the points in the balloon were like in this small space, incredibly small space, right? So that's exactly the Big Bang theory. The universe is now expanding, is inflating. So many years ago you can quickly do a math and calculate okay, so therefore since it is expanding at this rate, therefore it was in an incredibly small space 13.8 billion years ago. Boom, we know when the universe was formed, 13.8 billion years ago. Simple as that. And and now okay, so if that is the case, if that is what we think is correct, then it should be able to predict the future of the universe, correct? Like if I'm doing this backward calculation, like if the universe is expanding at this rate, how much smaller was the universe billion years ago, then I can do the same. Like if the universe is expanding at this rate, how much uh, farther away the galaxies will be maybe 5 years later or 10 years later. And indeed the Big Bang theory can actually successfully predict a number of predictions for the future of our universe. Like the Big Bang theory has made countless predictions that has actually been proven to be correct. And therefore, the Big Bang theory is our most well established theory of explanation for how the universe was formed and when it was formed. And so, according to the Big Bang Theory, the universe was formed from an incredibly small space 13.8 billion years ago. Alright? So, any questions so far? This is the summary of the whole chapter that we're going to study. Okay, of course, you will have a lot of questions that we will slowly answer throughout the chapter. Um, oh, Rodro, class started like not long ago, like I think 30 minutes, 15 minutes ago. 15 minutes. 15 to 20 minutes. Yeah, when you joined, 15 minutes before that. So Singapore is around 5. Yeah, not exactly 7:35. It actually started at like 7:40. So, yeah. Why is there where we are super planet and a trillion billion years ago? Super planet. Will there would be or no any effect on us because of this equation? Why doesn't the gravity between the galaxies hold them together? Okay, so first question is, were we a super planet anytime billion years ago? No, we didn't exist billion years ago. This planet Earth only existed as long as the sun has been in existence, and sun has been in existence for not long ago. Like the Earth is only what, I think. Okay, how old is the Earth? I don't actually remember the exact value. Like how old is the Earth? Well, the Earth is only 4 billion years old. All right, so 4.5. So the Sun is like 4.6 billion years old. Okay, so 4.6 billion years ago the Sun was formed, and so 0.1 billion years after that the Earth was formed. But so like we didn't even exist back then. So yeah. Okay, that's that question. Will there would be any effect on us because of this inflation? Very good question. Will it affect us? Well, we can't really say for sure. Like, what would happen if the what would have? But the thing with the inflation is, in our scale, in our comparison, it is very slow. It's a very slow expansion because the inflation occurs like the rate of inflation is very slow compared to our lifetimes. Like it has the universe has reached its current size in 13.8 billion years, right? We don't exist. We like as a like even a entire generation exists for like what 100 years, 200 years, right? So like we don't actually feel the effect of inflation in the long run. Okay, is the galaxies were pulling by any black hole? Well, are the galaxy? Yeah, there are a few questions like that. Like, why are the inflation is occurring? The space between the galaxies is expanding. But you said what? You said gravity attracts. So the gravity of the galaxies should be pulling them towards each other, right? Well, yes, that's what our calculations say. Our calculations say that the galaxies should be pulling each other inward. The black holes should be pulling the galaxies. So the universe, if anything, should be contracting. But contrary to our calculations, the universe is actually expanding, and that actually does not make sense to us. And so what we suggest is that there must be some other energy that we do not know about, and that energy is causing the universe to expand. We don't know about that energy, so we call that energy dark energy. But actually, we just don't know about that energy. We just don't know much about it. Okay, almost we know nothing about it. We know nothing about it basically. Okay, we only have a few suggested explanations for it, a few hypotheses, if you will, but there is no perfect evidence or perfect conclusive theory about dark energy. There's no such thing. Yeah, like we don't know. Like we can see that gravity should attract, the universe should collapse, but the reality is the universe is expanding. We don't know why. Interesting thing to think about. Very interesting fact to think about. What is the rate of inflation? Again, that's a question for Google. So, what is the current rate of inflation of universe? Because otherwise, it will just give me money inflation. Well, the inflationary epoch lasted. Well, actually, sorry. Inflation is the wrong term because inflation right now it's called expansion. Inflation was called inflation when at the at its beginning stages. Now it's called expansion. The expansion of the universe. Um, the expansion. Oh, right. Why am I googling? Okay. About the current rate of expansion. Well, the current rate of expansion is not constant. It is increasing. Yeah, the universe is expanding, and the rate of expansion is actually increasing. We don't know why. Very good question, by the way. Does the expansion increases time in space? The expansion increases the space-time fabric. The expansion increases the space-time fabric. That's all I will say from for here. I'm not going to say more. Dark energy. What is the work of this dark energy? Is dark energy more powerful than? Well, we don't know. We don't know anything about dark energy. Is it more powerful than? All we know is that the galaxies should attract each other due to gravity, but that is not occurring. The galaxies are actually moving away from each other. So there must be some energy that is causing this motion, that is causing this expansion in space. So that energy we call it dark energy. We just don't know anything about that energy. Okay. And also, is our Milky Way galaxy moving from other galaxies? Yes, our Milky Way galaxy, just like all the galaxies, it is also moving away from all the other galaxies. By comparing the apparent brightness of distant standard candles to the redshift of their host galaxies, the expansion rate of the universe has been measured to be, yeah, that's a good value. It's about from Google, yeah, thank you. So 73.24 kilometer per second per mega per sec. Yeah, that's just a current rate of value. So, but it's been increasing. Okay. Anyway, that value actually is not much of significant for us right now. Okay. Okay. Now let's get back to the topic again for background information. So, since the 17th century, cosmologists had struggled with the problem that a universe governed by gravity alone would naturally collapse at a faster and faster rate. See, like what we are thinking now that okay, what you just asked 5 minutes ago that the galaxies should be attracting each other due to gravity. So since the 17th century, when it was 17th century, right? 17th century was Newton's time, right? Because Isaac Newton was what? Isaac Newton was around 1727. He died at 1727, and he was from 1643. So ever since Newton's law of gravity, ever since Newton gave his theory of gravity, cosmologists were like struggled that okay, you are saying every mass attracts other masses, and that theory holds. Newton's law of gravity can explain all of the Newton's laws of gravity and Kepler's theories. They can together they can all explain all the orbits. We studied this that the Earth is moving around the sun due to gravity. The moon is moving around the earth due to gravity, the other satellites are moving around other planets due to gravity, the sun is moving in the galaxy due to gravity. So gravity explains all of these forces, all of these motions. But also, a universe governed by gravity alone, if gravity is the only force in empty space, that's what we thought, then it will naturally collapse at a faster and faster rate, right? Because that universe will attract each other and then it will just collapse, right? However, even a naked eye glance at the night sky shows that our universe is mostly empty space. Correct? All right. So this is actually known as Olbers Paradox. Olber is one of the scientists who have wrote this. Many other scientists had wrote this, but this is known as Olbers Paradox. This is a paradox, right? It's like a paradox is a logical thought that doesn't make sense. Okay, it's a logical thought that doesn't make sense. So the thought is like this. Okay, so gravity attracts all the masses attract each other due to gravity. Fine. So the universe should collapse. But like whenever we use a telescope to look at the sky, it's mostly empty space. Well, that doesn't make sense. Well, the answer to this riddle came in 1929 when Edwin Hubble, very famous guy, remember this name, Edwin Hubble, made a series of observations of some very distant galaxies, all of them well outside the local group. Okay, do you remember what a local group is? Of course you don't. We started this long ago. So let me just remind you again. What was a local group? Well, the picture should be around here. Yeah. Remember this? Our place in the universe, right? So this is the Milky Way. The Earth is here somewhere, right? Revolving around the sun. And this is our local group, a group of galaxies. But if you look at other galaxies that are far beyond our galaxy, those are galaxies of other local groups. Okay, back to our topic. That was a little tangent over there. Okay, so what did Edwin Hubble do? Edwin Hubble, well, he made a series of observations of some very distant galaxies. So these are very distant galaxies, far away. So these are all well outside our local group. Okay. And then what he did, he took the light from those galaxies and he split those light into a spectrum. Okay. He split their light into its spectrum. What does that mean? What does splitting light into spectrum mean? Remember the diagram from Prism? Remember the diagram of dispersion? Like dispersion, you saw a diagram of dispersion in your book, I think in standard 8, and also in the chapter of light waves you may have seen it. I'll show you another diagram right now. uh, yeah, I think if you don't remember, that's alright. This diagram, let me just format the background to white. Can we have a white background? Yeah, please, white. Yeah, cool. Okay, so you see this diagram. If you give white light into a prism, it gets separated into many colors, right? This also happens to be the logo of the famous band Pink Floyd, if you guys know that band. So yeah, so that's a prism, right? So a prism can split light into many different colors. If you give white light into it, it shows you all the colors in that white light, because we know white light is composed of many different colors, right? So now this is something that will look like coming out from the prism, right? This is something that will look like it, like or red, orange, yellow, green, blue, indigo, violet, right? All of the colors of the spectrum. So kind of like this. Okay, now back to what we were saying. So he split the light into their spectrum. That's how you split light into its spectrum. So you take light from a star. Obviously that light is white, but you pass it through a prism. Then all the wavelengths are separated. Now he found that its wavelengths had all been stretched or shifted to the red end of the spectrum. Okay, he found that the wavelengths had been stretched or shifted to the red end of the spectrum. All right. Okay, so why the red end of the spectrum? Let me see. Is this explained here? No. Okay, so to understand this, we first need to understand a phenomena called the Doppler effect. Okay, so the Doppler effect is a phenomena that we are normally we are supposed to study in the which topic, in sound waves chapter, but now we are going to study the Doppler effect in this chapter because we want to study the redshift phenomena. So this is a little clip from Sheldon Cooper.
Demonstrate.
What else can so yeah,
Demonstrate.
okay, when do you hear this sound? When do you
Demonstrate.
usually hear the sound? Meow.
Demonstrate.
Well, you hear this sound when, like, like a really fast car approaching you. What do you hear? Like, "Ee." And then when it goes away from you, you hear, oh, right? So that sound, that change in sound is called Doppler effect. As just one example, it can be seen with any other wave. Okay, so what is the Doppler effect? Well, the Doppler effect is the apparent change in wavelength or frequency of a wave caused by the relative motion of the source of the wave and the observer. So we will study the Doppler effect in more detail in sound waves chapter, but for now just understand that the Doppler effect is the apparent change in wavelength. So it's not a real change, it's not an actual change in wavelength. For example, let's say a car is approaching you, okay, and the car gives a horn, like pong pong. That the sound of that horn is different if the car is stationary, if the car is approaching you, if the car is moving away from you. All right. So when the car is approaching you, there is a relative motion between the source, that is the car, and the observer, that is you. Because you are stationary and the car is approaching you. So it is moving. So there is a relative motion. Also, maybe you are stationary and the car is moving away from you. There is also a change. There is some motion. So whenever there is relative motion between the source of a wave, in this case the car, and the observer, in this case you, then there is an apparent change in wavelength or frequency. Apparent change. It's not a real change, it's an apparent change. Now, what happens when wavelength or frequency changes? Well, in case of sound waves, frequency determines the pitch of sound. Like this is a high pitched voice, and this is a low pitched voice. Okay? So, like when you talk in a really high tone, that's a high frequency voice, and when you talk in a really low tone, that's a low frequency voice. So this is like a low frequency voice, and that is like a high frequency voice. Okay, so that's change in wavelength or frequency of sound wave. Okay, so in case of sound wave, the change in frequency results in either high pitch or low pitch, that is high frequency or low frequency. So when the car is approaching, it is high pitch, so high frequency, like, and when the car is moving away, it's low pitch, that is low frequency. So, okay, is the Doppler effect clear? I guess, yeah, like very weird explanations, but I hope it makes sense. Like that's how the Doppler effect works. Okay, so for sound waves, when the car is approaching you, that is when the source of the sound wave is approaching you, due to the Doppler effect, the sound seems to be higher frequency than it actually is. And when the source, in this case the car, is moving away, the sound seems to be of lower frequency than it actually is. Now that you understand, hopefully, the Doppler effect for sound, let's apply that to light. Well, in case of light, the frequency determines the color of the light. The frequency and wavelength determines the color of the light. For example, blue light is high frequency, red light is low frequency, yellow is like kind of in the middle, violet is very high, red, orange, yellow. Red, orange are like, if I just show you this, red, orange, these are these are low frequency light waves, and blue, violet, these are high frequency, these are very high frequency light waves. Okay, so in case of light, the frequency changes the color depends on the frequency. Therefore, if the source is moving away from the observer, if the source is moving away from the observer, what will happen? Low frequency. So there will be an apparent decrease in frequency. There's an apparent decrease in frequency. So the frequency of the light received from a star or galaxy that is moving away from us, the light from that galaxy will be more red than it actually is. Does that make sense? For example, if light from a galaxy has a frequency of 2000 hertz, the actual if light from a galaxy has a actual frequency of, let's say, 200 hertz, and when I receive that light, maybe I see it as 150 hertz, that means I see the light as a lower frequency that it actually is than it actually is. I see the light as a lower frequency than it actually is. So the light that I receive is more red than the light that the star actually emits. Is that clear? So the light that the star emits, there's a difference between the light that the star emits and the light that I receive. Correct? Because the light that I receive is more red shifted. It's more on the red side because it's lower frequency. Therefore, if the source is moving away from the observer, due to Doppler effect, there's an apparent decrease in frequency and it is called a redshift. So the light is more red than it actually is. The light received is more red than it actually is. Okay, now the opposite case. If the source is moving towards the observer, there's an apparent increase in frequency and it is called a blue shift. Clear? So to recap, blue light is high frequency, red light is low frequency. When a source is coming towards you, the light from it is actually more higher frequency, like the light from it seems to be higher frequency than it actually is. Therefore, the light seems to be blue shifted. But when a source of light is moving away from you, then the light seems to be more red than it actually is, because the light that you receive is lower frequency than the actual frequency of the light emitted by the source. I know it's a lot of things at once. Try to grasp it in your mind very slowly. I tried explaining it as slowly as possible. Now, any questions? Okay, so to answer your questions, I just read all of your questions at once first. Yeah, so the first question is that the how does red the first question is, okay, there was a question from before that, like, is the universe becoming lighter, like less dense? The universe is not becoming, I don't know what you mean by lighter, but the universe is becoming less dense, that's for sure. Mass is not decreasing because the mass of the universe is actually, let's not talk about it, like, because there's like stars forming and then they are giving away energy. A lot of things are happening with regards to the mass. but the overall space that that mass occupies is increasing. So yes, it's definitely becoming less dense every day. And about the questions from this topic, redshift. Well, more red and light. Okay, light far away, more red. Light far away now. No, not light far away. You need to say light from a source that is moving away. There is a difference between light far away and the source moving away. For example, let's say the light bulb from you is now 10 feet away. Okay, the light bulb is 10 feet away from you. It doesn't seem red. Okay, but if a light bulb even close to you, if it is moving at a very high speed, now we cannot imagine it because we cannot by hand or by any instrument make a light bulb go as fast as almost light, right? We cannot speed it up as fast as a galaxy, right? We cannot give it that much speed. But if we could, then if a light bulb, that is if a light source is moving away at a very high speed, then it will be more red. And if a light source is moving towards, so again you said light closer, not light closer, light source of light that is coming closer, that's more blue than actual. I hope that makes it clear. All right, so to explain it again, red shift and blue shift. If the source of light is moving away from the observer, that is me, then there's an apparent decrease in frequency and it is called a redshift. So if the source of light, in our case the galaxy or the star, if the galaxy or star is moving away from us, from the observer, then it's the light that we receive will be decreased in frequency and that will be called a redshift. And if a source is moving towards the observer, then there will be an apparent increase in frequency and it will be called a blue shift. Okay, so far so good. Red shift and blue shift. Any questions? Oh, you all. So red shift and blue shift. I hope that's clear. Now let's move on to this equation. Let's see this equation. Okay, I'll get back to Hubble and his topic in a bit, but let's look at this equation first. So this equation is called the Doppler equation, the Doppler shift equation. It's very simple. Yes, refoul. That is precisely correct. Yes. How does the redshift look like? Well, we will see. It looks like this. I'll get to it in a minute. So, change in wavelength. So, let's look at this formula for now. Okay. So, there is a change in frequency. That means there is a change in wavelength, right? Now, look at this. Change in wavelength divided by reference wavelength. What is the reference wavelength and what is the change in wavelength? Reference wavelength is the original wavelength that we were supposed to receive. Okay, for example, in case of sound, the original sound of the horn, pa pa, that's what we were supposed to receive. But we don't actually receive that. We actually receive like me or meow, right? So we don't receive the actual wavelength. We receive a changed wavelength. So the original wavelength, the reference wavelength, the original wavelength is the reference wavelength. So the reference wavelength is the original wavelength that is emitted from the star, and the change in wavelength is the difference between the reference wavelength and the wavelength received. So lambda is the wavelength that we receive, and lambda naught, lambda 0 or lambda naught, lambda 0 or lambda naught, this is the reference wavelength. This is the wavelength that the star actually emits. Okay, and again this is the reference wavelength. So the change in wavelength divided by the reference wavelength, this ratio is equal to another ratio. What's that? The velocity of a galaxy, or I should say, the recessional velocity of a galaxy, that is v, divided by the speed of light, c. Okay, so the recessional velocity, what's recessional velocity? Recessional velocity, let me define it here, or maybe let me just define it in a new slide. Yeah. So let's call this recessional velocity. It is the speed at which a galaxy is moving away from us, the observer. A galaxy is moving away or towards us, moving away or towards us. Okay, so it's either moving away from us or it is moving towards us. So we are the observers. That's recessional velocity. So a galaxy can be either moving towards us or it may be moving away from us. As we know from Hubble's observations that all the distant galaxies are moving away from us. Correct? Okay. So this is the recessional velocity. It is the speed. It's actually a speed. It is the speed at which a galaxy is moving away from us. So this is the speed that we want to calculate, right? We want to know if a galaxy is moving away from us, how fast it is moving away. Then we know the rate of the expansion. And divided by c is the speed of light. So speed of light, c, there's nothing to explain about it. So I hope you understand this equation. Correct? Okay, any question? So regions are moving farther away. Red giants are moving farther away. No, when we talked about all the colors in the previous classes, we always talked about their original colors, not the colors that we see. Okay, when we say a red giant is red, we mean it's actually red. We mean its reference wavelength is red. Its reference wavelength is red, not the changed wavelength that we observe. Okay, since we know the Doppler shift, we can account for the Doppler shift as well. So when we, and actually for stars that we observe, we actually mostly we always observe stars within our galaxy or at least within our local group. But when we are talking about the Doppler effect, that we see for galaxies much more far away, like galaxies of outside our local group. So those are much far away. So that's more dramatic of a change. Okay. So don't confuse this topic with the other topic that we studied of red giant colors and everything. Those are actual colors. Those are not colors that we think they are. Those are actual colors. Okay. Is the light traveling at that speed or the star? No. Light always travels at this speed of light c, and the value is 3 × 10 to the power 8 meters per second. No confusion about it. Okay, this is the speed of light. That's what light travels at this speed. However, v is the speed of the galaxy. That is the recessional velocity of the galaxy. What's this velocity? It is the speed. V is the speed at which a galaxy is moving away or towards us, the observer. So, if a galaxy is moving away from us, at what speed? If a galaxy is moving towards us, at what speed? That speed is the recessional velocity, v. Hope that answers the question. How do we calculate the speed of galaxy? Or what was another question? I hope you understand the formula now. Are black holes also moving further away from us? Galaxies are moving further away from us, so the black holes of those galaxies are also moving further away from us. Yes, good question. How do we calculate the speed of galaxy? Very good question. How do we calculate the speed of galaxies? Well, we calculate them from this formula. Okay, we know the change in wavelength, we know the reference wavelength, we know the speed of light. We can calculate the recessional velocity from this formula. What color does the galaxy emit? Lambda naught. This color. This wavelength. Okay, this wavelength color. Very good question. Okay, now let me go into what is this redshift? What is happening here? Okay, so this diagram that you see here is a redshift of spectral lines in the optical spectrum of a supercluster of distant galaxies on the right, as compared to that of the sun on the left. So this is on the left that you see is from the sun, right? Let me just make this a little bit bigger for you so that you can read it properly. Yeah. So you see of distant galaxies is on the right. Okay, so this is distant. This is from a distant galaxy, and on the left we have the sun. This is a spectrum from the sun. Okay, and you can see a difference. Like the black lines are shifted. Okay, how we know the speed of light? There have been countless experiments. Very good question. How there have been countless experiments to determine the speed of light that we do not study in O levels, but we study on further our studies. But yeah, there are many different experiments to calculate the speed of light. Okay, anyway, one of the famous ones you can look it up is by using mirrors. Okay, I'm not going into details here. Okay, anyway, so look at these two diagrams. This one is from the sun, and this one is the from a very distant galaxy. Now understand the light from our sun. Well, we studied that the light from our sun is yellow, right? And we also see the sun every day as a yellow ball right up there in the sky, right? It's a yellow ball. So the light from the sun is yellow. Well, like I said, the sun, just like all those stars, even though we say yellow, we only call it yellow because the majority of its radiation is in the yellow spectrum. The majority is, so yellow is more intense, but light from the sun actually contains all of these colors. Okay, so again, if you put the light from the sun here in a prism, then it will disperse that light into all the different wavelengths. Okay, and then you can record all those different wavelengths and you will get something like this. Now the problem is, in the light from the sun we should get all the colors, right? All the wavelengths. That's what we expect, because the sun is having nuclear fusion reaction, and in those nuclear fusion reactions all sorts of electromagnetic radiation are given away, so all the colors of the spectrum should be observed. But we see a few black lines here, right? Why are there a few black lines? Well, these are the lines that are missing. These wavelengths are missing from the spectrum of the sun. Why are these wavelengths missing? Because the sun is mostly made of hydrogen. Okay, and hydrogen absorbs these wavelengths of light. Okay, hydrogen absorbs these wavelengths of light. How do we know hydrogen absorbs these wavelengths of light? Well, we can take in our laboratory, we can just take a cylinder full of hydrogen gas, transparent cylinder, and then we can shine light through that cylinder, and then uh, after that light has passed through the hydrogen, we can take that light and shine it through a prism, and then we can put it on a spectrum, and we will see exactly like the spectrum that we receive from the sun. That's how we know that the sun is made of hydrogen, and that's how we know that these black lines are because of hydrogen. Okay, so okay, hydrogen absorbs these lines, fine. Now a very distant galaxy, a supercluster of distant galaxies, from other informations, we know for a fact that majority of the gases in that distant galaxy is also hydrogen. In fact, in all galaxies, the majority of gases is always hydrogen, because hydrogen is the most abundant gas in the universe. Okay, so majority of the gases are hydrogen. Fine. Now, oh, by the way, you can also ask why hydrogen is the most abundant gas. Because it was the first gas that was formed, and also it is the easiest gas to form. Like I said, hydrogen. How do you form a hydrogen? You have a proton, you have an electron moving around it, boom, you have a hydrogen. Simple, very simple structure. Okay. Anyway, now, so the question is, light from that distant galaxy, if I shine it through a prism, I should also get the same spectra as the sun, because just like the sun, that galaxy is also mostly made up of hydrogen. That we know for a fact, no confusion about it. So, but the lines from the galaxy, the black lines, are not at the lines where we expect them. The lines are a little bit shifted, as you can see from this diagram. The lines are a little bit shifted, and they are shifted towards the red end, towards the red, right? They are shifted upwards in your screen. So that means they are shifted towards red. This is called a red shift. Okay, so there is a red shift in the spectral lines. There is a red shift in the colors that we receive from those galaxies. And since the spectrum from very distant galaxies show red shift, therefore, it must be that the galaxies are moving away. And that's how Hubble knew that all the galaxies are actually moving away from us. And that's what we were talking about here in the reading material when we said by splitting their light into spectrum, he found that its wavelengths had been stretched or shifted to the red end of the spectrum. Shifted to the red end of the spectrum. Naming this effect redshift, Hubble realized that it must be caused by all the galaxies moving away from us at great speed. And that was the first observation of the expansion of the universe. That is, all the galaxies are moving away from us in 1929. Thank you. Any questions so far? This is the point up to which we will study today. Any questions up to this point? How do we calculate the? Yeah, okay, I already answered these. Okay, why can something travel faster than light? Very good question, but it's way off the topic. So, send me a message on Messenger. I will give you a link to a excellent video by Fermilab explaining why nothing can travel faster than light. There are more explanations, but I find that one very fascinating. I'll send you that video. Please inbox me. Thank you. How a naked eye can see the color of lambda 0? What are you talking about? I'm not sure what you're talking about. Very good question though. Like, I think it's a very interesting topic. Please ask me in details in Messenger or somewhere. Okay. How do we how do we see the sun? I see black because my eyes hurt. Okay. How do we see the sun? Well, we don't directly look at the sun. That's harmful for your eyes. We don't directly look at the sun. What we do is we take light from the sun, pass it through a prism, and then look at it and the spectrum. Okay. How we understand the galaxy is moving towards us or moving from far from us? Yeah, just like I said, since we see redshift, therefore must be that the galaxies are moving away, because redshift only occurs if the source of the light is moving away from the observer, and in this case the galaxy is the source and we are the observer. So since we are observing redshift, that means the source, the galaxy, is moving away from us. Hope that answers the question. Sun is not yellow only, but why do I see black when I say? I already answered the question. Why Earth mostly contains nitrogen? The air of the atmosphere of the Earth mostly contains nitrogen. Yes. Well, why? Um, that's actually a very good question. I'll have to look it up and answer you. I don't know the answer right now. I'll have to look it up. That's a very good question. Thank you. What is the prism made of or composed of? The prism is just glass, a triangular block of glass, nothing else. What property gives it the ability to identify the color? Well, a prism actually doesn't identify the color per se. What it actually, a prism, what it does, it's a block of glass. So it does what a glass would. The glass is glass, and so glass refracts. Okay, to steal a line from, yeah. Anyway, so glass is glass, and glass breaks, but glass is glass, and glass refracts. Okay. Okay. So now, so glass refracts, but the refraction of different colors of light, as different colors of light have different wavelengths, they are refracted to different angles, to different degrees. Okay, so some light is refracted more, some light is refracted less. Red is refracted less because it has lower wavelength. Blue light is refracted more because it has higher wave. Sorry, I just messed up the wording. Sorry about that. Uh, Red light is refracted less because it has a longer wavelength and a lower frequency. But blue light is refracted more because it has a shorter wavelength and higher frequency. Therefore, since different wavelengths are refracted to different angles, that is how a prism actually splits light into all of its different wavelengths. How can we see the actual color of a star and say that it is lambda 0? Again, I'm not sure. What are you guys asking? Lambda 0. I'm not familiar with this. Lambda 0. Oh, do we have buffering? Lambda 0, I think it's something. I'm really not sure about lambda 0. Please enlighten me later and I'll answer. Maybe I'll be able to answer that. Anyway, moving on. What is on the. Please try to ask questions related to the topic. Thank you. What is on the other side of the black hole? We don't even know what's inside the black hole. What do you mean other side? How do you even know there's an other side to the black hole? How do you even ask that question, right? Right. Prism is made of, okay. Lambda O. Okay, but what is lambda O? Oh, you mean lambda naught? Oh, okay. I got you now. Okay, so the reference wavelength. Just say the reference wavelength. How do we know the reference wavelength? Well, we know the reference wavelength lambda naught or lambda 0 because as we know what the star is made of. So we know, for example, a sun-like star is made up of hydrogen. So we know that it will mostly emit, since a sun-like star is made up of hydrogen. So we know definitely that its spectrum must look like this. So in this spectrum, these black lines are lambda 0, because these are the lines that we expect, right? So these are lambda 0 and these are our actual wavelengths that we see. The actual wavelengths that we see are different from the wavelengths that we expect. So this is the difference. Okay, so let me just draw it here and that will make sense to you, I think. For example, this will be let me copy it from here. Yeah. Okay, so the reference wavelength, this is our reference wavelength, and this is the actual wavelength that we see. So this is our reference wavelength, this is the actual wavelength that we see, and the difference between the two is the difference between the two is the difference. So there's a gap, right? So like if I draw a line from, let's say, here to here, so this gap is equal to, let me just make it a little bit more, yeah, so this gap, let me also draw a line so that it's clear to you. So yeah, this difference is the delta lambda. This difference is the delta lambda. Okay, so yeah, yeah. So this is lambda naught. This is the reference wavelength. This is lambda. This is the wavelength that we observe. This is the wavelength that we expect because of hydrogen spectra. This is the wavelength that we get, and so the difference is the delta lambda. That is the change in wavelength. This one. Okay, so this is the delta lambda. I hope that is clear. All right. How can we see the actual color of a star and say that? Okay, okay. So why the Earth contains mostly nitrogen? That's actually a very good question, but unfortunately I can't answer that right now. I don't know. Class is will be over. Class is officially over. I'm just answering your questions for a few more minutes and then I'll end it here. I'll end it here if you don't have any more questions because class is over for today. Okay. All right. No, no. Like, don't think about nightmare minutes. Don't worry about it. This is it. Up to I won't go further to the next slide in this class. Okay. So if you don't have any more questions, I will end it here. Thank you very much for your time and attention. Okay, I guess you don't have any more questions. Oh, 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 we are actually having buffering. Yeah, okay, it's fixed now. Let me get back to the final questions. That is, what is the age of the universe? Already answered that, 13.8 billion years ago. Why the Earth? I've answered it 3 times already. Why does the Earth contain more? I don't know. It's a very good question, but I don't know. I'll answer it later. Okay, let me just end with one last question. That is, the what is lambda zero and how do we determine it? Well, if you look at here, for example, in case of a distant galaxy, we know that it must be the spectrum, the light from that galaxy must be identical to the light from our sun, because all galaxies are also mostly made up of hydrogen. So the light from that galaxy originally, what the light from that galaxy is originally is the original wavelength. That's the reference wavelength. So lambda zero is the reference wavelength. So in our case, the original wavelength emitted by that distant galaxy is the same as the wavelength of the sun, correct? Because the sun, the spectrum, the wavelength that we see from the sun corresponds to the hydrogen spectrum, and also the light that we see from a distant galaxy, that must also correspond to the hydrogen spectrum. So the light from both both lights should be identical. So the reference wavelength is the wavelength that it should be, which is the hydrogen spectrum, which is this one. This is the wavelength that it should be. But the wavelength that we receive is not the wavelength, the actual wavelength. We receive a different wavelength, which is lambda. So we receive this lambda, but we expected to receive this lambda naught. So this is the reference wavelength, which is the sun, or in our lab hydrogen spectrum. This is a default hydrogen spectrum. We can do it in our lab. We can take it from the sun. Same thing. But this is the lambda is the original, lambda is the actual wavelength that we receive from a very distant galaxy. And there is a difference between these two wavelengths. That difference is delta lambda, this much. Okay, in next class we will see some values of these lambda 0 and lambda, and we will do some calculations. Then it will be much more clear, hopefully. Thank you. Okay, so that's it for today. Okay, the connection's back on, and yeah, so that is it for today, I guess. I guess you understand lambda 0 and lambda difference now. So, and then I will end it here. Thank you. Allah Hafiz.